Good morning, my dear students. Today I am going to talk about the continuation of a current electricity chapter. In the previous class, already explained about the introduction of a current electricity, what is electric current, what is current density, what is drift velocity and mobility, the relation between current density and drift velocity. Right, that is, these topics are already explained in the previous class. So, now you are very familiar about that, right. Now, I am going to explain next topic, Ohm's law, from the chapter current electricity. Right, Ohm's law. Before going to this, suppose let us consider a conducting wire, or let us consider a conductor or conducting wire. So, this is conducting wire having uniform area of cross section, Suppose the area of cross section of the wire is taken as A, and the length of the wire is taken as L. L, length of the conducting wire, and A, area of cross section of the wire, So, this is a conducting wire having uniform area of cross section, right. Suppose this wire is connected to the battery like this. Right. So, a conducting wire is connected to the battery. Battery provide a potential difference of V across the ends of the wire, right. So, due to this potential difference, an electric field is created within the wire, right. So, when the conducting wire is connected to the battery, which provide a potential difference V across its ends, due to this potential difference, an electric field is created in the wire. So, suppose let it be E, and this electric field is always directed from the point having higher potential to the point having lower potential. Suppose this wire is denoted by XY, right. Here X end of the wire is connected to the positive terminal of the battery. So, this end maintaining higher potential, and this end is connected to the negative terminal of the battery. So, this end maintaining lower potential. The electric field is always directed from the point or end having higher potential to lower potential. So, this is the direction of electric field. So, electric field is directed from X end of the wire to Y end of the wire, right. And due to this electric field, electric current is constituted in the wire. Suppose this electric current is denoted by I, and which is flows through the circuit, right. And one more thing, the direction of a flow of current is also along the direction of electric field exists, or electric field created in the wire. Already we know that the direction of a conventional current is always along the direction of a flow of positive charges, or otherwise opposite to the direction of a flow of electrons. So, for example, if the free electrons in the metallic wire is travels from Y end to X end, the electric current constituted in the wire flows from X end to Y end. So, the direction of a conventional current is opposite to the direction of flow of free electrons, right. And this current is always directed along the direction of electric field created in the wire. The direction of flow of current is along the direction of electric field, right. And next, it was experimentally found that when the potential difference applied across the two ends of the wire is changes, the magnitude of current flowing through the wire also changes. It was experimentally found that if the potential difference applied across the ends of the wire is changed, the magnitude of current flowing through the metallic wire or metallic conductor also changed, right. So, there is a relationship between potential difference and electric current. The relationship between potential difference and electric current was first established by George Simon Ohm, a German physicist and mathematician. George Simon Ohm was the first one established the relationship between potential difference and electric current, right. According to George Simon Ohm, suppose if the temperature of the metallic wire or temperature of the conductor, suppose T is constant, if the temperature of the metallic wire is constant, then the magnitude of current flowing through the metallic wire is directly proportional to the potential difference applied between the ends of the wire, right. So, according to George Simon Ohm, the temperature of the metallic wire is maintaining constant. At that condition, the magnitude of current flowing through the metallic wire is always directly proportional to the potential difference applied between the ends of the wire, potential difference applied between the ends of the wire, right. So, it means if the potential difference applied between the two ends of the metallic wire is increased, then the current flowing through the metallic wire also increased. If the potential difference applied between the ends is decreased, the magnitude of electric current flows through the metallic wire also decrease. So, that is why the magnitude of current is directly proportional, I mean flowing through the metallic wire is directly proportional to potential difference, right. So, this condition is only applicable if the temperature of the metallic wire is constant. If the temperature of the metallic wire is constant, then only this condition is applicable, that is I is directly proportional to V, right. I is directly proportional to V, or I is equal to constant into V. If you want to remove proportional, we should introduce a constant, right. So, this constant is called conductance of the conductor. Conductance of the conductor. Suppose the conductance of the conductor is denoted by G. Conductance of the conductor is denoted by G. Therefore, I is equal to G into V. G into V, right. The reciprocal of the conductance is nothing but reciprocal of resistance of the conductor. The reciprocal of resistance of the conductor is nothing but conductance. Later we will discuss about that, what is resistance and what is conductance, right. So, but here the conductance of the conductor is equal to reciprocal of resistance of the conductor. Substitute Z is equal to 1 divided by R here, then I is equal to 1 divided by R into V, or otherwise V is equal to I into R. V is equal to I into R. So, this is Ohm's law, or this equation is called macroscopic form of Ohm's law. The macroscopic form of Ohm's law is V is equal to IR. What is V? Potential difference between the two ends of the conductor provided by the battery, right. I, the magnitude of current flowing through the metallic wire due to this potential difference, and R, the resistance of the metallic wire, So, V is equal to IR is called Ohm's law, or this equation is called macroscopic form of Ohm's law, right. So, it is from this equation or from this condition, it is clear that at a constant temperature, the steady current or constant current flowing through the conductor is directly proportional to the potential difference between the ends of the conductor, between the two ends of the conductor. So, this is known as Ohm's law. So, once again I repeat, Ohm's law states that at constant temperature, the steady current flowing through the metallic conductor is directly proportional to the potential difference between its ends. At a constant temperature, the magnitude of current or steady current flowing through the conductor is directly proportional to the potential difference between the ends of the conductor. Potential difference between the ends of the conductor. So, this is known as Ohm's law. The condition for Ohm's law, V is equal to IR. V is equal to IR. V potential difference, I electric current, and R resistance of the conductor. Here reciprocal of resistance of the conductor is nothing but conductance of the conductor, right. So, the macroscopic form of Ohm's law, that is V is equal to IR equation, can be derived from the equation J is equal to sigma into E. Here J is equal to sigma into E, this is microscopic form of Ohm's law. J is equal to sigma into E, microscopic form of Ohm's law, whereas V is equal to IR, macroscopic form of Ohm's law. The macroscopic form of Ohm's law, V is equal to IR, can be derived from the microscopic form of Ohm's law, that is J is equal to sigma into E. J is equal to sigma into E, right. Here what is a J? J is nothing but it's called current density. Current density. What is current density? The magnitude of a current flowing for unit area of cross section of the conductor. The magnitude of a current flowing for unit area of cross section of the conductor is known as current density. Current density is denoted by J. It is given by the formula J is equal to I divided by E. J is equal to I divided by A. Its unit is ampere meter power minus 2. The unit of current density is ampere meter power minus 2. The equation of current density is J is equal to I divided by A, right. And what is the sigma? This is electrical conductivity. Electrical conductivity. Later we will discuss about that, right. And E, electric field. Electric field or electric field established in the wire or electric field created in the wire. So, relation between current density, electrical conductivity and the electric field is J is equal to sigma into E. This is called microscopic form of Ohm's law. From this equation we can derive the macroscopic form of Ohm's law, that is V is equal to IR. V is equal to IR, right. Listen, here the area of cross section of the given metallic wire is uniform. So, the electric field created in the wire also uniform. So, this is uniform electric field. There is a uniform electric field created in the entire wire, right. We know that there is a relationship between potential difference, electric field and distance, that is V is equal to E into D. The relation between potential difference and the electric field is V is equal to E into D. Okay. So, already we know the expression. This equation is discussed in the first chapter, that is electrostatics. V is equal to E into D, or otherwise E is equal to V divided by D. This is relation between electric field and potential difference, right. D, distance. So, in this case instead of D we can write the length of the wire, that is L. So, this equation can be written as E is equal to V divided by L. E is equal to V divided by L, right. Now, substitute E is equal to V divided by L in this equation in the microscopic form of Ohm's law. So, then this equation becomes J equal to sigma, instead of E, V divided by L. V divided by L. So, J is equal to sigma into V divided by L, right. J is equal to I divided by A, because the current for unit area of cross section of the conductor is nothing but the current density. So, J is equal to I divided by A. So, I divided by A is equal to sigma into V divided by L, right. Just to rearrange this equation like this, V is equal to I L goes to numerator, L divided by sigma into A. Sigma into A. V is equal to IL divided by sigma into A. Right. In this equation, the quantity L divided by sigma into A is called resistance of the conductor. Resistance of the conductor. Resistance of the conductor or a resistance of the metallic wire or conducting wire, right. So, V is equal to I into L divided by sigma into A. In this equation, L divided by sigma into A, this quantity is called resistance of the conductor. The resistance of the conductor is denoted by the letter capital R. Resistance of the conductor is denoted by capital R. So, capital R is equal to L divided by sigma into A, or is equal to L divided by sigma into A, right. So, put instead of L divided by sigma into A to R, then this equation becomes V is equal to IR. So, this is Ohm's law or macroscopic form of Ohm's law. So, this equation is obtained from the microscopic form of Ohm's law, that is J is equal to sigma into E, right. J is equal to sigma into E, microscopic form of Ohm's law, and V is equal to IR is a macroscopic form of Ohm's law. So, Ohm's law states that at a constant temperature of the conductor, the magnitude of current flowing through the conductor is directly proportional to the potential difference between the ends of the conductor, potential difference between the ends of the conductor, right. So, this is equation for Ohm's law, right. So, in this equation V, potential difference, I electric current, and R resistance of the conductor, resistance of the conductor, right. What is the resistance of the conductor? Generally, resistance means the opposition given by the conductor or given by the material to the current flow or to the electric charges is known as resistance. Resistance is nothing but the opposition offered by the conductor to the current flow or to the electric charges is known as resistance of the conductor, resistance of the conductor. But it is defined as the ratio of potential difference between the two ends of the conductor to the current flowing through the conductor. The resistance of the conductor is defined as the ratio of potential difference applied between the two ends of the conductor to the current flowing through the conductor, If you know the magnitude of or steady current flowing through the metallic wire, okay, and the potential difference applied across the two ends of the wire, these two values are known, we can calculate what is the resistance of this metallic wire by using the relation R is equal to V divided by A. From that equation, the resistance of the conductor is defined as the ratio of potential difference between the two ends of the conductor to the current flowing through the conductor, But generally, resistance is nothing but the opposition offered by the conductor to the current or to the electric charge, But the definition, ratio of potential difference to the current, right. And unit of resistance is ohm. This is a symbol of unit of resistance, that is ohm symbol, and unit of resistance is ohm. This is SI unit. And another unit of resistance is volt ampere inverse. Volt ampere inverse is another unit of resistance of the conductor. SI unit of resistance of the conductor is ohm, but another unit volt ampere inverse. Resistance of the conductor is defined as a ratio of potential difference applied across the ends of the conductor to the current flowing through the conductor, right. Suppose this is a variable power supply or variable battery, that is the potential difference applied between the two ends of the conductor can be varied by using this power supply. Suppose if the potential difference is varied, okay, 1 volt, okay, 2 volt, 3 volt, 4 volt, 5 volt, like that. According to Ohm, if the potential difference is applied, across the conductor is changed, then the magnitude of current flowing through the metallic wire also change, right. Suppose for 1 volt potential difference, the magnitude of steady current flowing through the metallic wire is, for example, 0.5 ampere. 0.5 ampere. If the potential difference is 2 volt, the current becomes 1 ampere. If the potential difference is 3 volt, the magnitude of current becomes 1.5 ampere. Similarly, for 4 volt, 2 ampere, for 5 volt to 2.5 ampere. 2.5 ampere. So, this condition is only applicable, already I told, the temperature of the metallic conductor remains constant. The temperature of the conductor remains constant. If the temperature constant, if the potential difference is increases, automatically the magnitude of current flowing through the metallic wire also increased. Right. Now, draw a graph by taking potential difference along the x-axis and the corresponding current is taken along the y-axis. Right. Now, draw a graph by taking potential difference along the x-axis and the current along the y-axis. Right. So, here the given wire is a conducting wire. For conducting wire, the nature of voltage current graph is a straight line and which is passing through the origin, right. So, the materials for which the voltage current graph is a straight line, then they are said to obey Ohm's law. That is the material said to obey Ohm's law. The material which obeys Ohm's law are called ohmic materials. For ohmic material, the nature of voltage, potential difference and the current graph is a straight line which is passing through origin. So, if any material which obeys Ohm's law, then the graph is drawn between voltage and the current. The nature of the graph is a straight line. Those materials are called ohmic material. Because those materials are obeys Ohm's law. Right. The materials which does not obey Ohm's law are called non-ohmic materials. Right. For example, all the conductors are ohmic material. Because all the conductors obeys Ohm's law. If the graph is drawn between voltage and the conductor for conductors, the nature of the graph is a straight line. Okay, it means the conducting material conducts the electric current linearly. So, that is why the nature of the graph is a straight line. But the material which does not obey Ohm's law are called non-ohmic materials. Example, all the electronic devices are non-ohmic materials. For example, diode. Diode is one of the non-ohmic device. Because the diode does not obey Ohm's law. So, that is why it is non-ohmic device. For non-ohmic device or for non-ohmic material, the nature of voltage and current graph is like this. For non-ohmic device or non-ohmic material, for example, diode, the graph is drawn between potential difference and the electric current. The nature of the graph is like this. It means the diode is a non-linear conductor of electricity. It does not conduct electricity linearly, but all the conductors conduct electric current linearly. That is why the nature of the graph is a straight line which is passing through the origin. But the non-ohmic material does not obey Ohm's law. So, that is why the nature of the graph is not a linear line, not a straight line. Instead, it is a curved line. It shows the diode conduct electricity non-linearly. Okay, this is because the resistance of the diode is not constant. How can you calculate the resistance of the diode and resistance of the given material? By taking slope. In the VA graph, if the slope is drawn on the straight line or a curved line, we can get or we can calculate what is the resistance of the material. Because slope of the VA graph is equal to reciprocal of resistance. reciprocal of resistance. So, by taking slope in the VA graph, that gives reciprocal of resistance of the conductor or a reciprocal of resistance of the material, right. Here, if we take a slope on this linear line at any 2 points, the resistance of the given metallic wire is always a constant. The resistance of the metallic wire or conducting material is always a constant. But if the slope is drawn in this graph at various position like this, the resistance value is not constant. The resistance value is not constant because this is not a linear line. So, for a linear line, the slope is always constant, but for non-linear line, the slope is not constant. If slope is not constant, then resistance value also not constant, right. So, for ohmic material, what is ohmic material? The materials which obeys Ohm's law are called ohmic materials. For ohmic material, what is the nature of potential difference and current graph? Straight line, which is passing through origin. If we take a slope for this straight line, that gives reciprocal of resistance of the given material, reciprocal of resistance of the given material, that value is always constant. What is non-ohmic materials? The materials which does not obey Ohm's law are known as non-ohmic materials. For non-ohmic materials, the nature of a graph is not a straight line. This is a curved line. If we take a slope, the slope value is not constant. So, the resistance of that is non-ohmic material also not constant. It varies continuously, right. So, this is the main difference between ohmic materials and non-ohmic materials. It was experimentally found that the resistance of the conducting material or resistance of the material is directly proportional to length of the material or length of the wire. The resistance of the wire is directly proportional to length of the wire. It means, if the length of the wire is increased, suppose its length is L1 and its length is L2 and its length is L3. If the length of the given wire is increases, then its resistance value also increases. Here L3 is greater than L2 and L2 is greater than L1. Similarly, R3 is greater than R2 and R2 is greater than R1. It means, if the length of the given material of the wire is increases, the resistance value also increases. If the length decreases, resistance value also decreases. So, that is why the resistance of the wire or resistance of the material is directly proportional to length, right. And also, it was found that the resistance of the material is inversely proportional to area of cross section. For example, for a given length of the wire having different area of cross section, for a given length, its length L, its length also L, length same, but area of cross section of this wire is suppose A1 and its area of cross section is A2 and its area of cross section is A3. So, same material, same length, but different area of cross section, right. Here area of cross section of the third wire is greater than second wire and area of cross section of the second wire is greater than the first wire, right. So, length same, but area of cross section different. So, due to this change in area of cross section, the resistance of the wire also changes. So, R1 resistance of the first wire having area of cross section A1 and R2 the resistance of the second wire having area of cross section A2 and R3 the resistance of the third wire having area of cross section A3, but all the three wire having same lengths, right. Here the resistance of the third wire is less than the resistance of the second wire. The resistance of the second wire is less than the resistance of the first wire. It means if the area of cross section is increases, the resistance value decreases. Resistance value decreases. So, that is why the resistance of the material is inversely proportional to area of cross section. Resistance of the wire is directly proportional to length. Directly proportional to length. Now, combine these two conditions, we can get R is proportional to L divided by A. R is proportional to L divided by A, right? Or R is equal to constant into L divided by A. R is equal to constant into L divided by A. This constant is called electrical resistivity of the material, electrical resistivity of the material or electrical resistivity of the conductor. It is also called specific resistance. Specific resistance, right? Electrical resistivity or specific resistance of the material is denoted by the letter rho. Electrical resistivity is denoted by the letter rho, right? So, now this equation can be written as R is equal to rho L divided by A. So, resistance of the given metallic wire or material is given by the formula R equal to rho L divided by A. R is equal to rho L divided by A. What is rho? Electrical resistivity. Electrical resistivity of the material. Electrical resistivity of the material. L length of the material and area of cross section of the given material. Right. Here, the reciprocal of electrical resistivity of the material is nothing but conductivity of the material. Conductivity. Conductivity or electrical conductivity. So, electrical conductivity is defined as reciprocal of electrical resistivity. Reciprocal of electrical resistivity is called conductivity, right. So, R equal to rho L divided by sigma into A. 1 divided by rho is equal to sigma, therefore, rho equal to 1 divided by sigma. Rho is equal to 1 divided by sigma. So, instead of rho 1 divided by sigma, then this equation becomes R is equal to L divided by sigma into A. R is equal to L divided by sigma into A. So, resistance formula R is equal to V divided by I. If you know potential difference and electric current, we can calculate resistance value by using this relation. If you know the resistivity of the material, length of the material and area of cross section of the material, we can calculate the resistance by using this relation. Suppose the given values are length of the material, area of cross section and electrical conductivity, we can calculate a resistance by using this relation. So, resistance is nothing but the opposition given by the material to the current is known as resistance. The resistance, okay, different formulas. R equal to V by I, R equal to rho L divided by A, R is equal to L divided by sigma into A, right. Already I told the unit of resistance is ohm. The unit of resistance is ohm, right. And rho electrical resistivity is also called specific resistance. It is denoted by the letter rho. L length of the conductor and A area of cross section of the conductor, right. Suppose let us consider a conductor of length L equal to 1 meter and area of cross section A is equal to 1 meter square. That is, this conductor having unit length means 1 meter length, and this conductor having unit area of cross section. Unit area of cross section means 1 meter square area of cross section is called unit area of cross section. So, for a given conductor having unit length and unit area of cross section, substitute L equal to 1 meter and A is equal to 1 meter square in this equation, the resistance equation. R is equal to rho L divided by A, L equal to 1 meter. So, therefore, R equal to rho L value 1 and A value also 1. Therefore, rho is equal to R. That is, electrical resistivity is equal to resistance. It means electrical resistivity means the resistance offered by the conductor, to the current flow having unit length and unit area of cross section, If the length of the conductor is 1 meter and its area of cross section is 1 meter square, then the resistance offered by this conductor is called electrical resistivity. Electrical resistivity. So, electrical resistivity is defined as resistance offered by the conductor to the current flow having unit length and unit area of cross section, having unit length and unit area of cross section. And unit of electrical resistivity, that is rho, is ohm meter. The unit of electrical resistivity is ohm meter. Ohm meter. The reciprocal of electrical resistivity is called electrical conductivity. The unit of conductivity, that is sigma, is ohm inverse meter inverse. Ohm inverse meter inverse, or symbol like this. Ohm is a unit of resistance. Ohm meter is a unit of resistivity. Ohm inverse meter inverse is a unit of electrical conductivity. So, resistance is defined as ratio of potential difference between the two ends of the conductor to the current flowing through the conductor. Resistivity is nothing but the resistance offered by the conductor to the current flow having unit length and unit area of cross section. The reciprocal of electrical resistivity is called electrical conductivity. The electrical conductivity unit ohm inverse meter inverse, electrical resistivity unit ohm meter, and unit of resistance is ohm, right. The materials are classified into three categories based on their resistivity. So, based on resistivity, the materials are classified into three types. They are, first one, conductors, second, insulators, third, semiconductors. Conductors, insulators and semiconductors. So, these are classification of a material based on a resistivity, right. First, conductors. The materials having resistivity in between 10 power minus 6 ohm meter to 10 power minus 8 ohm meter are called conductors. If any material having resistivity between these two values, then they are in the conductors category. So, any material having resistivity in between 10 power minus 6 ohm meter to 10 power minus 8 ohm meter are called conductors, right. And second, insulators. The materials having resistivity in between 10 power plus 8 ohm meter to 10 power plus 8 ohm meter to 10 power plus 16 ohm meter are called insulator. If any material having resistivity between these two values, then they are in insulator cadre, right. Conductors resistivity range 10 power minus 6 ohm meter to 10 power minus 8 ohm meter, and for insulator the resistivity range is from 10 power plus 8 ohm meter to 10 power plus 16 ohm meter, right. And third, semiconductors. The material having resistivity in between 10 power minus 4 ohm meter to 10 power plus 2 ohm meter are called semiconductors. The semiconductors are the material having resistivity in between 10 power minus 4 ohm meter to 10 power plus 2 ohm meter, right. So, 10 power minus 4 to 10 power plus 2. So, conductor resistivity range 10 power minus 6 to 10 power minus 8. Insulator resistivity range 10 power plus 8 to 10 power plus 16 ohm meter, and semiconductor resistivity range is from 10 power minus 4 ohm meter to 10 power plus 2 ohm meter. So, these are classification of a material based on resistivity, right. Okay, conclusion. First, Ohm's law. What is Ohm's law? According to George Simon Ohm, at a constant temperature, the steady current flowing through the conductor is directly proportional to potential difference between the ends of the conductor, the two ends of the conductor. The microscopic form of Ohm's law, J is equal to sigma into E. J current density, sigma electrical conductivity, and E electric field. So, this equation is called microscopic form of Ohm's law. From this equation, we can derive the macroscopic form of Ohm's law, that is V is equal to IR. Already we derived. So, V potential difference, I electric current and R resistance of the conductor. What is the resistance of the conductor? Resistance generally opposition offered by the material to the current is known as the resistance, but it is defined as ratio of, from this equation, V is equal to IR or R is equal to V divided by A. The ratio of potential difference between the two ends of the conductor to the current flowing through the conductor, and another expression for resistance R equal to rho L divided by A. From this equation, it is clear that the resistance of the given conductor is directly proportional to its length and inversely proportional to area of cross section, right. Here rho electrical resistivity of the conductor, What is electrical resistivity of the conductor? Electrical resistivity of the conductor is defined as resistance offered by the conductor to the current flow having unit length and unit area of cross section, right. The reciprocal of electrical resistivity is called conductivity. The reciprocal of electrical resistivity is called electrical conductivity. Here electrical conductivity and electrical resistivity, these two are depends on the nature of the material, but they are does not depends on the dimension of the material. Dimension means length and area of cross section. It does not depends on the length of the material and area of cross section of the material. They are depends on nature of the material. Nature of the material means copper, aluminum, iron. Okay, for copper, one value of electrical resistivity value and the conductivity value. The same length for same area of cross section, for different material, correspondingly their resistivity and the conductivity values are changes, right. And one more thing, the electrical resistivity and the electrical conductivity also depends on temperature. So, factors affecting the electrical resistivity, and conductivity are temperature and nature of the material. If the material changes, resistivity and the conductivity value also changes. If the temperature changes, resistivity and electrical conductivity value changes, but does not depends on length and area of cross section, or does not depends on dimension of the material, but factors affecting resistance and conductance, temperature, nature of the material, length of the conductor and area of cross section. The length changes, resistance and as well as conductance value change. If area of cross section change, resistance conductance value change. Temperature changes, resistance conduction value changes. If the nature of the material changes, the resistance conductance changes. But electrical resistivity does not depends on length and area of cross section. They are depends on temperature and the nature of the material.